This is a video walkthrough of the code to run a repeated measures t-test in R. To start with, we will be using a dataset contained this time in a package, the Datarium package. So we first need to load this package up, and we will be using the mice2 dataset, and this is set up in order to run a repeated measures t-test. So we'll take this data set and we'll assign it to an object named mice. So if we run that, we see it ran down here, and then if we look over in our environment, we see under data, we have this thing called mice. It's a data frame. It has 10 observations of 3 variables. And if we wanted to see what it looked like, what those variables were, we can use the head function and put in our data frame, and it will give us the first 6 rows as well as the column names. So what we see here is the first 6 rows and the column names. So we can see that we have an ID column. So this is a generic ID for each of the 10 mice. We have a before weight in grams, and we have an after treatment weight also in grams. One of the things that we will need to do is calculate a difference between those 2 columns, those 2 before and after columns, our 2 time points, because that's what we're actually going to be testing, is the difference. So we can calculate this right here. So what this is saying is, in our mice data set, we are saying with the $, make a column called diff or difference. And that doesn't exist yet, right? So we only have ID before and after. But we're going to make it exist with this. And we're saying this is what needs to go into that difference column, that diff column. We want you to please take the after column and subtract from it the before column. And so what it will do is it will take each after, subtract it the before, and add in, put that difference in that diff column. So if we were to run this, we see, okay, it ran. If we look over here at our data, now we have 10 observations of 4 variables. And we can check our work right here with another head function. And we can see we still have our ID, our before, and our after. And here is our difference column, the diff column. And you might notice that I did after minus before. You will, I promise, get the same results if you did before minus after, because the distribution is going to be the same. So now that we've calculated this difference column, we can get descriptive statistics. So we will be using the describe function from the psych package. So we'll go ahead and call that package and give it a second. Down here we can see, and it'll say, okay, the package is attached. And now we'll use this describe on, again, that difference column that we just calculated. When we run that, we get our statistics down here. So we see that we have a total N of 10. This is the mean difference, remember. Standard deviation, min, max, range, skew, and kurtosis. Next, what we'd like to do is kind of check some of the assumptions, the normality, what it looks like. Are there any outliers, things like that. We'll start with the outliers, move on to normality. And so to test visually if there's any outliers, what we'll do is we'll look at a box plot. So we'll be using ggplot for this. So we'll go ahead and call ggplot. And then here is where we're creating our box plot. So this first line right here is our call to ggplot, and it's saying ggplot, please look at the data mice. And for the aesthetics, so what should we have for our x and our y? The y value is going to just be the difference, so that diff column. And then for the x, we don't really want you to look at anything, but if we don't put it in, then you get grumpy, so we're just going to put in something empty. Then we're going to say that we would like a box plot, please. And we're also going to say that we would like to have our data points plotted on this box plot and have them be slightly spread out so we can see them. So when we run this, it will think about it for a second, and we have our box plot over here. So again, this is just the difference. We're looking at, are there any extreme outliers? The way that we're going to determine that is, are there data points above or below these little whiskers sticking out here? We can see that, there's one right on the edge here, one right on the edge there, but nothing that we would consider an extreme outlier. So our visual check turns out pretty good, and we'll move on now to some normality checks. One way that we can check the normality is to do a Shapiro-Wilk test. And again, this is being performed on the difference column. And so we call shapiro.test on the difference column of mice, and we get our output right down here. And so we see this is the data that we used, that difference column. This is the Shapiro statistic. This is the p-value. And since it is not significant, it's greater than 0.05, what we would say is that the distribution of the difference is not significantly different than a normal distribution. And so this test would indicate that we have satisfied that normality assumption. We can also make a histogram to visually inspect the normality. And so we've already called ggplot, so we don't have to do it again. But this time we're doing a histogram. So we start with our ggplot call. We feed it, we feed it the data. And here we're saying that we want the x value to be the difference. And then at the end here, we say we would like a histogram with geom histogram, and we don't have to put anything within those parentheses. So if we run that one, we get another plot here. And so here's the difference down along the bottom. And each of these is a count, in this case, of 1. And we can see it seems to be pretty spread out. With, an n of only 10, it's slightly more challenging, but we can see seems to be spread out. Another way that we can visually inspect our data for normality is using a QQ plot. And we can use both a regular QQ plot and a detrended QQ plot. To do this, we do need to call QQ plotter, the package QQ plotter. So we'll go ahead and do that. And then we will perform a regular QQ plot first. So this makes use of both ggplot and the QQ plotter package. They kind of nest in with each other very nicely. So we start by a call to ggplot, and we define our data. So we say data equals mice. That's the data set we'd like to use, please. And then we define our mapping and our aesthetics right here. So we say sample is the diff column. So that's what we're looking at. And then these three are coming from that QQ plotter package. So this is talking about the banding of the QQ plotter, and the alpha is how transparent or not. This is not the same thing as like a p-value alpha. This is the transparency. This is our confidence interval. So what kind of confidence interval do we want for those bands? The band type, so do we want like an identity line? And then what color fill do we want? And then here again is what type of line we want. So we said identity equals true. And then this is our point color, so each data point, it's going to be plotted. And here we're saying we want those data points to be black. This is a labeling line, so we want our x-axis to be labeled as theoretical quantiles and our y-axis to be labeled as sample quantiles. And theme underscore black white, or BW, sorry, is referring to the background of the plot and what kind of grid lines you can and cannot see. When we run this, we will see what it looks like right here. And what we're looking for is for our data points to fall neatly along this normal line, normal distribution line, and certainly for them to fall within this 95% confidence interval. And what we can see is that they fall quite neatly along this line and certainly within the confidence interval. So this would indicate, again, that our data are quite nicely normally distributed. We can also do a detrended QQ plot. So this would be how far outside of normal are each of the data points. And all that we have to do is, it looks the exact same as this one. We are just adding dtrend equals true to each of these. And so when we run this one, we get another plot. And that is what this is. So this is, here's our normal distribution and how far off it might be. Again, we would really like for our dots to line up neatly along this line, and then certainly within the 95% confidence interval. They look pretty good, so we would say our data appear to be normally distributed. To run the repeated measures t-test, we would use the t.test function. And here is the t.test function. We are defining our x and our y, so after minus before. And we are saying that, yes, it is a paired t-test. So if we were to run this, it says you just ran a paired t-test. And this is the data that you used. Here's your t-statistic, your degrees of freedom, and your p-value. And, indicating, yes, that is a significant difference. It also gives a confidence interval and a sample mean difference. And just as an illustration, you absolutely do not have to do this, but if you were to switch the before and the after, you would get the same statistics. So if we were to run this one, I'm just going to scoot this up so we can compare. There we go. You can see our t-statistic is the same in absolute value, right? Our degrees of freedom are absolutely the same. Our p-value is the same. And our mean difference is the same in absolute value. Same thing for our 95% confidence intervals. So it's just whether or not there's a negative in front of these. But at the end of the day, the significance and the t-statistic are going to be the same. So it really doesn't matter in which direction you run it. Whatever makes the most sense for you. Next, what we can do is calculate Cohen's d. And we can do that with the effect size package. And with this, though, we will need to transform our data into a long format. So rather than having a before column and an after column, we're just going to have a weight column. So we'll have to use tidyverse for this because we need the pipe function right there. And so what we're going to do is we're going to say this is our new data right here, our mice underscore long. That's just saying in long format. And here we're saying please take the mice data set, but only columns 1 through 3. So we're effectively excluding that difference column with this. Take those 3 columns, send it on here. We need to gather right here. And what we're gathering by is the weight here. So these last two arguments are what columns we're gathering. So that's what we're putting together. This is what is going, that's what it's going to be called now. And then key equals group is the key column name. So what we're using to reference. So if we run this and then look at it, what we can see now is we still have our ID column, but now here is our key argument. So key equals group, and we'll have a before group, and then we'll have an after group. And then value equals weight is pulling all of those weights into just a weight column. So to calculate an effect size using the effect size package, the Cohen's d function from that, we'll first call the effect size package. And the reason why we went through all this is because the Cohen's d function requires data to be in a long format. So we couldn't have used the data the way that it was before. So it's still thinking about, there we go. So what we'll do is we'll say Cohen's d as the function. We'll define our data. Notice how we're referring to our new format data. We'll put in our formula. So weight by group, and then we'll say that it is a paired test. So when we run this, we get a Cohen's d of 8.08 and a 95% confidence interval around that of 4.37 and 11.8 effectively. So that would be considered a large effect size for this test.